In this problem, a transfer function is given and it is mentioned that it is for a phase lead compensator. Okay. For that we have to find the maximum phase shift. Function of a phase lead compensator. GCS equal to 1 plus 3TS upon 1 plus TS. Okay. For this, find maximum phase shift provided by this compensator. See the solution. Now, if we look at the face of this, it is equal to tan inverse 3t minus tan inverse t. 3t omega tan inverse t omega. Okay, because I can write my GS in terms of g omega 1 plus 3t 1 plus j t omega. Okay, from this I can derive this. Now, to get the maximum phase for such phase lead compensator, I can differentiate with respect to omega. Okay, and equate that to 0. When I equate this to 0, I will get some value of omega. That value of omega, if I find the phase, that will be the maximum phase. Okay, or otherwise maximum phase shift can be directly obtained using formula, which is sin phi m equal to a minus 1 upon a plus 1, where a is equal to 3 in the given expression. So phi m is equal to sin inverse 3 minus 1 upon 3 plus 1, which is equal to sin inverse 1 by 2 equal to pi by 6. This is the maximum phase shift provided by this compensator. Okay. Another question number 6. In this, a state equation is given. Okay, and we have to find the state transition matrix. A linear system is described by the following state equation. A x into a plus b ut. Okay, matrix A is given by this. Find state transition matrix. Solution. See, if I found the Laplace transform of the state equation, then I can write s into xs is equal to a into xs. Okay, plus B into US. From this, I can just find if my input is 0, then excess common S minus A. Okay. Now, the state transition matrix is equal to Laplace inverse of Si minus A. Okay. So, and Si minus A is equal to S0 0 S minus 0 1 minus 1 0, which is equal to S minus 1 1 S. Inverse of Si minus A is equal to S 1 minus 1 upon S square plus 1. You can see just once again. I have found Si minus A. This Si minus A is equal to this. The inverse of Si minus A is Ss minus 1. Sign of this diagonal element will change, and that divided by the determinant of this matrix. So 1 upon S square plus A is divided by the whole matrix. Okay. This matrix is nothing but the adjoint matrix. Adjoint matrix upon the determinant of the matrix. Okay. Now I have to find the Laplace inverse of 1 upon S square plus 1 S minus 1 1 S. Okay. This is equal to S upon S square plus 1 minus 1 upon S square plus 1 1 upon S square plus 1 S upon S square plus 1. I have to find the Laplace inverse of this, and this and this. So this has got Laplace inverse cos t minus sin t cos t. This is my state transition matrix. Simple. Just again involves only mathematics. Okay. Next question which has appeared in CATE 2006 is linked question from the control system. Linked question. Okay. In this, first we will see the statement and try to understand the problem. Consider the unity gain feedback control system whose open loop transfer function is given. Okay, this is open loop transfer function for the system. The first part of this linked question is, let this be question number 7. Find the value of A so that the phase margin of the system is equal to pi by 4. Pi by 4. Okay. So we have to find this. Now to see the solution for this, if I want to find a phase margin, I should know the gain crossover frequency. Okay, so the gain crossover frequency is the frequency at which gain is 0 dB or gain is equal to 1. This is my g of j omega. So magnitude of this must be equal to unity, must be equal to under root of a square omega s square plus 1 upon omega s square. Okay, so on finding this, I will get a square omega s square plus 1 equal to omega to the power 4. So this will be quadratic in omega to the power 4 minus a square omega square minus 1 equal to 0. Substituting, let assume that omega square equal to t, I'll get t square minus a square t minus 1 equal to 0. T value is nothing but a square plus minus under root of a to the power 4 plus minus 4ac, so that will be 4 upon 2. This implies my omega value will be under root of a square plus minus under root of a to the power 4 plus 4 upon 2. Okay, now looking for the phase margin. When I substitute this omega in g of j omega, I can write minus tan inverse j omega minus 180 degree. Okay, this is equal to pi by 4 or this is equal to 45 degree. Okay, now substituting this value of omega here and calculating the value of a will give me, we can easily find the value of a. Now see, solution of this is not very easy because if we don't have a calculator, it will become a very tedious job. So in this case, what we can do is, out of the 4 options which were given, value of a given as 2.4, 1.4, 0.84 and 0.74. Select any one of these value and try to substitute back in the question. Okay, on substituting, the one value of a will satisfy that, so that particular value is the answer for this. Okay, presently the answer for this is 0.84. Second part of this question, let that be question number 8. Now with this value of a, with the value of a set for phase margin of pi by 4, we have to find the value of unit impulse response of a open loop system at t equal to 1 second. Find the value of unit impulse response of the open loop system at t equal to 1 second. Okay, we have to find the value of the unit impulse response. Now we have to find it for the open loop system. A value is 0.84. Okay. Now suppose this is my xt, gs and yt. xt is given as unit impulse response, so my xs will be 1 because xt is delta t. Thus ys is nothing but xs into g of s. This will be equal to 0.4 upon s plus 1 upon s square. Okay, so this will be equal to 0.84 ut plus t ut. This is my yt. I got this yt while finding the inverse Laplace transform of this particular equation. Inverse Laplace transform of this equation will give me my yt. So my yt is this. So I have to find the value of yt at t equal to 1 second. So yt at t equal to 1 is equal to 0.84 plus 1, which is equal to 1.84. Simple. So this is the answer for the second problem. Yes, this is related to the first problem because in the first problem the value of a whatever I have found, that value is used in solving the second problem. Okay. So this was a linked problem which has appeared in GATE 2006. Now the following set of problems have appeared in GATE 2007. The first problem is 1 mark problem. I'll just start again from 1. In this, a transfer function, a closed loop transfer function of a control system is given. Closed loop transfer function of a control system Ts equal to s minus 5 upon s plus 2 s plus 3. Okay. Then 4 options are given and we have to choose the correct one. The first one is whether the given system is, the transfer function for the given system is for unstable system, uncontrollable, third is for minimum phase, fourth is for non minimum phase. Okay. See, the closed loop transfer function is given by this. Just understand, since the poles of this closed loop transfer functions lies on the left hand side of S plane, just write down the points. Since poles are lying on left hand side of S plane, thus system is stable. If system is stable, definitely it is controllable. So first two options are not there. Second, if we looking at the face of this function, then if all poles and zeros lies on the left hand side of S plane, then the system is minimum phase. System is minimum phase. Else non-minimum. Looking at the transfer function given in the question, the zero which is there present, it is lying on the right hand side of the S plane, and both the poles lying on the left hand side of the S plane. Thus All zeros plus poles are not lying on the left hand side of the S-plane. Thus, it is a given transfer function is for non-minimum phase system. It is for the non-minimum phase system.